I'm just checking my audio. Please let me know if it's loud enough.
Audio is quite, yes, sir.
Oh,
Audio is quite
thank you.
clear. Okay. Okay.
Good morning, ladies and gentlemen. We have virtually gathered here for the second day of the international webinar on recent explorations in complex systems, dimensions, and atomic physics, Recap 21. One song can change a moment, and one prayer can change the impossible. Let's begin the webinar with a prayer song, followed by a word of prayer by Dr. S.T. Pushpalata Gracelyn, Assistant Professor of Physics.
Bless the Lord, oh my soul, oh my soul. Worship His holy name. Sing like never before, oh my soul. I worship Your holy name. When the sun comes up, it's a new day dawning. It's time to sing Your song again. Whatever may pass and whatever lies before me, let me be singing when the evening comes. Bless the Lord, oh my soul, oh my soul. Worship His holy name. Sing like never before, oh my soul. I worship Your holy name.
Prayer. Dear Heavenly Father, we thank You for this new day. Thank You for all the blessings, especially the health which You have showered upon us. Father Lord, today we are connected virtually in this webinar session and pray to You for guidance, knowledge and wisdom. Bless the resource person, all the staff and students who are participating. Let the time be very useful to all of us so that we may gain more knowledge in this particular field of physics. Lord Jesus, bless us and keep us all through today. In Jesus' name we pray. Amen.
Thank you. Small cheer and great welcome makes a merry feast, said William, to welcome the virtual gathering and to introduce the speaker of the day.
Good morning, everyone. It is my privilege to introduce and welcome today's resource person, Dr. N. Nirmal Tyagu, Assistant Professor of Physics, Madras Christian College, Chennai. He has research interest in areas like nonlinear dynamics and complex systems, complex networks and topological analysis, and experimental soft matter physics. He finished BSc Physics in American College, Madurai, and MSc and PhD in IIT Madras. He has various experience as assistant professor, research associate, and postdoctoral researcher. He had served in VIT Chennai, IIT Madras, Max Planck Institute for Dynamics and Self-Organization, Germany, Rutgers University, New Jersey, USA, and S.N. Bose Center for Basic Sciences, Kolkata. He has 11 international publications in reputed journals to his credit. He has organized many workshops, seminars, and symposium, and also has been resource person in several conferences and seminars. He is serving as reviewer in reputed journals like Physical Review Letters, Physical Review E, and American Journal of Physics. He has also earned so many awards and honors and cleared NET and qualified in GATE also. Really, sir, we are happy to have such an enthusiastic, dynamic personality in our midst in this international webinar Recap 21. We are eager to listen to your talk on an invitation to the physics of complex systems. On behalf of the Department of Physics, Sarataka College Autonomous, Tirunelveli, I extend a warm and cordial welcome to you. I also welcome all the participants to this virtual gathering. Welcome to you one and all. Now, may I request Dr. N. Nirmal Tyagu to take over the session. Thank you.
So, thank you so much, ma'am, for this very kind introduction. I have a mic which is just disobeying. I don't know. We'll give it a try. I want to see how the feedback is. Hopefully you can hear me because I'm trying to couple things through the phone as well as this. Can you hear me, ma'am? Anyone? Do you sound enough?
Yes, sir.
Yes. Okay. So, yeah, thank you so much. I would like to really, appreciate this invitation, and I'm very glad to be here amidst this wonderful gathering of this. And my heartfelt thanks goes to the principal, Usha Godwin ma'am, our HOD Jagati Jasmine ma'am, and the organizing secretary, Vardhini ma'am. So, and of course, a great welcome to all the student participants who are enthusiastically listening to this seminar. This is quite a topic where I will not be able to go very deep within to bring out the richness of it, but it's kind of a guided tour. When you go to a new city, you just want to know what are the great sites to see. If you land in New Delhi, some sort of sort, do a little bit of justice to that. Okay, so let's just go with the flow, metaphorically, right? So we are talking about complex systems and complex systems, the physics of complex systems. Truly speaking, complex systems is a very rich interdisciplinary field, and physics has contributed lion's share to the development of complex systems. You can see all kinds of people working in mathematicians, statisticians, biologists, ecologists, chemical engineers, mechanical engineers, aerodynamists, aerodynamicists, and linguists. All these people are working in. Okay? So this is what the bird flocks are. Okay, I'm going to stop the movie and show you that this is a complex system. This is one beautiful example of a complex system. I'm going to take you to the next example. So here is firefly. Fireflies are these small bugs that have chemicals which keep reacting, and then it gives out light. So photoluminescent chemicals are there, which it's able to, using which it's able to fire. Now I'm going to show you a movie, some glimpses through the movie where you can really see what's happening, and then you will be able to appreciate it. So it's the Great Smoke Mountains National Park. So you can already see that these things are firing all over, and the kids are holding it. Yeah. So this is your firefly. You can just start to emit. Now, what is that we are going to show is a very unique behavior, which is going to be seen now. You can see that there are these random flashes, seemingly random flashes, but then just watch out. Soon it'll turn out to have, there is going to be an instance where it'll all try to synchronize. I think here you will see that. It just happens in one moment. It's going to synchronize and come out, synchronize, fall back. So this is very, very beautiful. If you look at the real forest, no, everything will synchronize at one moment and then it'll desynchronize, sync, desynchronize. This is another example. I'll tell you why this is interesting. Okay, what the fireflies can teach us. Why should we go and look into a forest? And what is so great about it? Why should we even think about this when we talk about complex systems? So if you take a single entity, this entity in this case is your firefly. So the firefly is here, which emits light after a certain amount of time. Okay, there is a period to that. It doesn't do anything. So as this observation says, if it takes 12 periods, it's going to emit again. That's how it does. Now, one weird thing that happens is that if you happen to see one firefly with a group of others, then it won't just like that emit irrespective of what the other guys are doing. It is going to watch out what the neighbors are going to do. And it's going to adjust its clock. So there is going to be kind of a interaction between this guy and the other guy, this guy and the next guy. So there's going to be a kind of a interaction. And in terms of statistical results, we might call this as a mean field. All of you would have learned mean field at some point in statistical mechanics. So what the others do start to influence you. What you do, it influences the others. So this kind of an interaction gives way to something which you cannot expect when a single entity is considered. That's the whole point behind the complex systems. Okay? Single entity will behave quite predictably, but the moment you put in too many entities and then you fix a simple interaction rule, the richness is not quite describable exactly. And that gives all the beauty to the physics of complex systems, if I may say. The lessons are direct. One thing, starting with our brain, with our endocrine hormone system, the heart, everything goes in unison. Not in the sense that your brain and the heart and the hormone systems are going to work together. No, brain itself is a collective of neurons, right? So each zone or each region in your brain is going to fire together. The motor region, the learning region, there are memory regions and all. So all of them have to function in unison. And that means that the individual neurons, because in the brain, the individual entity is a neuron. And that neuron needs to couple with the neighboring neuron, with the neighboring neuron, with the neighboring neuron, and so on and so forth. So there is a collective which needs to form, and then they all need to fire at the same time. We don't fully understand. But then what the firefly teaches us that, yeah, if you put this together, if this kind of a picture, metaphor can be invoked, perhaps we will understand how brain is able to function. Likewise, the heart is also having this sino-arterial node where all this electrical signal comes in a periodic fashion. There's a lot more richness to the heart, which I'm afraid that I cannot go in. If you look at the heart, they are not strictly periodic. There is a signal of chaoticity in it. If they're not chaotic, again, there's going to be some problem. Again, the brain, it doesn't completely work periodically. In fact, a healthy brain should not work periodically. It should have some chaoticity in it for it to function normally. If there is a periodicity, strict periodicity, then the brain normally goes through an epileptic episode. Epilepsy is this fits, people get fits if they get these periodic bursts in the brain. So chaos, so to say, we're going to define what chaos is. Chaos is this deterministic, unpredictable behavior, is a hallmark of natural systems. We call this as an emergent dynamics coming from individual entities that follow simple rules and that interact in some predictable fashion. All right. So this is the Firefly story. Now, all of this is not going to the entire talk. We are not going to deal with it. We are going to just come down to very, very simple things. So to say, let me just summarize. Individual entities, they exhibit simple behavior, but the moment you put in more than one and you start tweaking their interaction a bit, just like real systems, you have this emergence, and that's the complexity. Now, complexity shouldn't be misunderstood. Normally, people would think that, okay, complex is something that always goes with the imaginary number I. That need not be the case always. In this case, it does not mean complex numbers. Okay? Complex systems do not have any link to complex numbers. That's a math. Beautiful quote of Aristotle: "The whole is more than the sum of its parts." That describes how complex systems and their emergent behavior, hierarchical organization excellently. One of the major things which we have to really acknowledge is that all this kind of interaction happens to be nonlinear in nature. And these nonlinear interactions are generally manifested as these rich behaviors. And rich behaviors are quite varied, and most popular science will always tell you about self-organized behavior, chaotic behavior. And the lesser known things are these rare events and adaptive interaction, which we won't go much into. So remember that if you're talking about complex systems, it's because of the nonlinear interaction between simple entities. And we are not going to talk about quantum mechanical chaotic systems or complex systems. Most of the systems which the complex systems community study is just classical mechanics, right? At the turn of the 19th century, people thought classical mechanics is completed, the study is completed, and rest of it is going to be stamp collection, right? And then the new revolution of dynamics came in the later part of the 20th century, and then now we are having this new physics, so to say. So this is your complex systems. And don't confuse complex with complicated. The dictionary meaning is not going to render us anything result. What are the rules? And there is a way to simulate and find out. Okay. So complex is something that we have some traction of the underlying physics. Complicated is no. We are nowhere close to understanding what's happening in a system that is complicated. All right. Okay. The world starts so simple. And we're going to see that it's not that simple with this beautiful example of simple pendulum. All of us know this, that the simple pendulum is so simple, that's why we call it simple, right? We start off this. T is 2 pi root of L by G. Any child knows if it's gravitational field of acceleration due to gravity as G. Now, this is taken too much for granted because, when you take the actual Newton's equation and solve it, we do not acknowledge the fact that there is a sine theta. Most of the time, we are mostly dealing with a case where sine theta is approximated to theta, which renders us this equation. That is true only for small amplitudes away from the equilibrium. In fact, this picture is somewhat deceiving because small should basically stop here. Already what I have drawn for small is large. So what about this? What about the pendulum going up here? We are going to be in huge trouble if we don't consider sine theta as theta. And for people, one can easily recall that sine theta is a nonlinear term. Now, what do I mean by nonlinear? Until you do this Euler expansion, sine theta is theta minus all the higher order terms, and the higher order terms are nonlinear. So if you retain only theta, yeah, you can deal with this. Otherwise, you cannot. And the relation which we saw earlier is not going to hold true. T is 2 pi times root of L by G is true only for theta small. For theta large, you cannot say this. You need to replace the 2 pi with an elliptic integral. So all the elliptic functions, elliptic integrals come into picture. And you don't have to get afraid of this. It is not the sine function. The behavior of the pendulum is not going to be sinusoidal anymore. With the larger amplitudes, you will see the deviation. The bold curve which we have plotted here is the deviation which is given by that elliptic integral, and that is going to be the case for higher amplitudes. So increased amplitude, you're going to see discrepancies, and the discrepancy is the deviation from the sine wave. Why this is so? That's because for small oscillations, you are going to see ellipse in the phase space. So I have plotted P versus Q. This is called the phase space. Now, for smaller amplitudes, I'm going to see nice, beautiful sine waves. If I plot these ellipses in theta versus t, I'm going to see sine waves. Now, if I increase the amplitude larger and larger, I'm going to go closer to this red curves. These are called the separatrices. Separatrices meaning that you're going to isolate oscillations from the rotations. You go as close as to an angle at which you're going to start only seeing oscillations. Now these oscillations will take to go from this position to above and then come back. It's going to go up and stay for some time and come up. So these regions which we are seeing here, these are the regions where highlighted. So this region, these are the regions where it's going to slow down. That slowing down is not accounted when we go with the regular exercise. So this is a good way to understand how our simple pendulum works. Okay, here is a missing term which I think somewhere. Okay, there is a partial minus sign which you can always look up this reference for the entire term. Now let me go one step higher in terms of complexity. Already I have established the fact that the simple pendulum which we take it to be simple is not that simple. Now let's go into the case where there's a double pendulum. What is a double pendulum? You take one pendulum, attach it. This is a rigid rod. Put another pendulum, which is a rigid rod. Either you can do it that way or take two metal plates, put a pivot, and this is a metal plate and this is a metal plate. So here is a pivot and here is a pivot. You can do that. Now, I'm going to show a movie which I have made from my lab where you will see a double pendulum is going to be released from rest. Two movies I'm going to show. You're going to take a careful look at that movie and you're going to write down how many number of times the pendulum, the M2, so to say, M2 is going to move anti-clockwise and how many number of times it's going to move clockwise. If you see anti-clockwise, you just write A. Immediately after that, again, if it is going to do anti-clockwise, you write another time A. So you write the sequence of anti-clockwise, clockwise, anti-clockwise, anti-clockwise, clockwise. So you just bring out in paper and then follow the second movie. Do a similar exercise. And then it's a self-assessed quiz. I'm going to show the answer on the next page. You tell me whether you're going to see any difference. Okay, both the movies are taken for almost the same initial condition. We're going to see how different the motion is going to be by doing this exercise. Are you all ready? Okay, we are going to have some quiz during this talk. So you have to be ready. So all you need is a pen and a notebook. So if you don't have it, just go and grab it. Okay, so I think the students will be enthusiastic to begin this. Okay, I'm going to, okay, for the benefit, I'm going to wait for a couple of more seconds and then restart it. Okay, I'm going to start it. Start it now. So please note down. So this is anti-clockwise, clockwise, anti-clockwise, clockwise, clockwise, anti-clockwise, anti-clockwise, clockwise, clockwise. Okay. So this is done. Hopefully, most of you would have written down the sequence. I'm going to go to the second movie. Almost the same setup, same initial condition. We'll see how that sequence works out to be. Let me just expand this a bit and then restart it. Are you all ready?
Yes.
Okay. Look at this. Clockwise, 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 anti-clockwise, 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 anti-clockwise. Okay. Okay. Hope you all got the pattern. I revealed the answers, okay? Because many of you may not be that familiar, but I helped you observe. That was my task. If you can start observing, you can easily pick up a lot of things, right? I'll show you the answer, check if it matches with. So if you take the movie 1, starts with A, C, A, C, C, A, C. Look at movie 2, it starts with C, 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 A. It just goes on 7 times before it comes back to C. Right? So what I'm trying to impress here is that you start the system exactly the way it is, but then it's going to show you quite unpredictable behavior. That is a hallmark of a nonlinear system, and we're going to see why it is so. Now, if you look at the double pendulum, I have plotted the trajectories of theta 1. Theta 1 corresponds to only this angle. Theta 2 is even more, it might look a bit more messy to you. So I'm not going to impress that data and ask you to infer. So I have started with 3 initial conditions. And those 3 initial conditions are going to evolve with time. And you can see that they are all separating from each other quite soon. Just this position. This position M2 would have already gotten up far away from us. And this is another hallmark. Initial condition, sensitive dependence to initial condition, and exponential separation. Okay, quickly we'll just see what is chaos. This is a mathematical definition. Okay, F is transitive, periodic points are dense, sensitive dependence on initial condition, which I'm not going to run a course. So I'm not going to ask you to digest this. I'll give you a very, loosened up definition, which perhaps you can remember this. You have deterministic equations. The system behaves ergodically. Ergodically meaning that it's able to access all the phase space. So people might think that it's like noisy system. In a very, very rough sense, you can think that it's equivalent to noisy, but it is not noisy because it has deterministic equations. One of the major hallmarks is that it is sensitive to initial conditions. So chaotic systems are distinguished by sensitive dependence on initial conditions, and they evolve through the phase space that appears to be quite. If you can understand this much, that's fine. So here is a very funny picture you might remember from this old movie of Kamal Hassan and Vasool Raja MBBS, in which Kaga Radhakrishnan is bound to get this coin pocketed. If in case he misses it, that's it. Okay. Now here is sensitive dependence to initial condition. You will not forget this example. If he misses slightly, it's not going to hit. It is never going to pocket it. This is your sensitivity to initial conditions. Small change in delta. Good. Okay, I've dropped a bomb here. I already impressed the audience that a simple pendulum is not simple. A double pendulum is completely out of bounds. And what about the weather? Weather is such a complex system that you can never ever hope to understand just because of the interactions, because of the nature of nonlinear interactions, because of the nature of sensitivity to initial conditions. But then this is what we study, right? So one of the first systems that we are exposed to when we study nonlinear systems is this model. If we can model the weather system with the most simplest of the features, then we have already succeeded. If we can replicate what happens in weather, if we do that to the model, we have already succeeded. So weather is overwhelmingly complex, but then the job of simplifying the essence has been a success. And that was done by Lorentz long ago, more than 50 years back. He came up with 3 equations. And this system is known as the Lorentz system. It's a 3-dimensional equation with these parameters. And this is your Lorentz attractor, or the butterfly attractor, which is quite ubiquitous. Now, here is a tool for the students who might want to explore. So you can go and Google up this called Chaos for Java. You can install in your computers and start playing. I'm going to just show you one instance. Okay, so this is your Chaos for Java. So I'm going to click ODE orbits, and I'm going to see this. So I'll show you one instance. Orbit 1 is 15, 10, 40. I'm going to type this 15, 10, 40. Let's just check the value, 15, 10, 40. If I put the same value, it's going to give me the same orbit. So I'm going to shift it only slightly in the second decimal place. Okay, this is my orbit. If I evolve it, let's see how it works. So I'm going to evolve it a bit slowly. I'm going to type enter. Let's see how the movie evolves. So you can see that red and blue, these 2 trajectories corresponding to 2 different initial conditions are going together. Now they have separated, they have joined in, they're separating, and so on. I'm going to run another time. So this time I'm going to make a very small separation in the x-axis. Okay. It's already evolved. So I want to rerun the movie. It's together, red and blue. 2 trajectories are running together, and then it has separated. They are separated, joining together. So this is a beautiful illustration of the richness of nonlinear systems. And the Lorentz system is still very deeply studied. It's being used as a test bed to study all the new properties of whatever system we take in. So students might just like to explore. And Chaos for Java has many other interesting things. So you might just want to go and check out. All right. So this is one resource, takeaway resource for all the students. Okay, let's move on. I'm going to, keep coming back to the simplest problems to impress upon you that physics is quite challenging. I'll take one more second to show you how challenging it is. Here it is, the 2-body problem. Thanks to Newton, we know that this is the equation, the force equation. Second show. You have a sun, you have Earth. World is pretty simple. You may not agree that cannot live in a world where there's only sun and earth. Why not? We put in the moon. Just bring in the moon. The moment you bring in the moon, Newton has to pack his bags, meaning you cannot write a closed form equation, which will give you the position or the force or the velocity of any object at any point in time. I repeat, this is not going to be solvable exactly. This is the classic three-body problem in the history of physics that doesn't have a closed solution. What is a closed solution? This example with the two-body, this has a closed solution for the force, but similar equation cannot be written for the three-body. Surprising. Every time I see this, it's so inspiring. And people have come up with various methods, geometrical methods, to deal with this, qualitative methods to deal with this. That is the job of Poincaré. That is the job of many distinguished physicists during the last century. And they came up with these methods. And these were the seeds to the modern development of nonlinear dynamics. Now, in order to impress upon you that why this doesn't have a closed solution and what kind of motion you will see with the three objects together in place, I'm going to show you a simulation where you're going to see three objects placed in the vertices of a triangle and allowed to move under the gravitational attraction. And you're going to see how complex the dynamics are. Okay? The dynamics is going to be. Here it is. These three things, they are tracing a trajectory, and then it's going to trace really, really intricate pattern. But it is not going to be so simple because it's not solved. There are much more to it. A lot of literature on it. It's a very rich problem. Okay. Okay. So this you can see it in Wikipedia. This simulation is taken off from Wikipedia. That's what I put in here. Now, hopefully, I have transmitted you how difficult the job is. Having one more object in the presence of two objects will give you all the complexity. Now, what about the real world? The real world is not just three-body, it's many-bodied system. And those many bodies can be extended to continuum, like fluids. Fluids is continuum mechanics. Aerodynamics is continuous mechanics. Continuum mechanics. Turbulence, no hope of finding a solution. That's what Feynman said. So all this is because of the interaction which we are talking about. Let me now take you in a slightly different area, the many-body dynamics. How interesting these are. We may not really appreciate on a daily basis. Do we have to worry about all this? So in order to show you, kind of sightseeing trip into the world of granular media, I invite you to this world of granular media. Everything that we use as human beings, the materials that we use predominantly is in the form of grains, is second only to water. Food, rice, fruits, vegetables, parcels, medicines, all of them are in granular form. And these are interesting systems because we don't have constitutive equations. At least fluids are better. Continuum is better. We have Navier-Stokes equation, which can completely define the playing ground. But in terms of in the world of granular media, we don't have equations. Thanks to statistical physics, we have some models, some paradigms where we can model these grains as forced dissipative systems, and there are some equations which one can use to extract some features of it. Okay. This is beautiful. Right? Sand can behave as a solid. You stand on it. The moment you take it in your hands, it's going to flow. So it's going to behave like a fluid. Not just that, it is also going to behave as a gas. Look at the sandstone. It's going to be fluidized and it's going to go follow. There's a lot more richness to this. Let's not go deep into that. I want to bring you back for the benefit of students to some fundamental problems. Imagine that I'm going to give you a box of candies, a jar of candies. And you're all well aware of the solid state physics, which you learned how to pack spheres. You know the volume of the jar, you know the volume of individual candies. Assume sphere is the shape of the candies. Don't even worry about ellipsoids. You take spheres of known volume. You take a known volume jar. If I give you the jar, can you find out how many candies are there? I won't tell you because I packed it. I won't tell you. By measuring the height or measuring the volume, how much it has occupied the candies, can you figure out the number of candies contained in the jar? This is a question. Anybody can open the mic and say, or else you can, type in. Is it possible or not? You just say yes or no. That's all.
Approximately, like if in 10th standard we were this problem was
Okay.
given and
If
perhaps it was
you happen to
solvable.
have an answer, yes, you can write it in your page because it's a self-assessment. I'm going to give the answer. If you say no, write down the reason why you think no. And then you match with my answer. Okay. This is a problem which, one can easily relate with the greengrocer. The vegetable market you go, there is a greengrocer who is selling vegetables and fruits. He was also arranging things in piles. Now, the richness of the problem and the answer which I'm going to give is going to stagger you. If you think you can count the candies by knowing how much height the candies have occupied, you're going to get it entirely wrong. So you will never be able to find out how many candies are there just by knowing the height of the vessel which it is locking in. And this you might know from your solid state physics that if you can pack the candies either in the face-centered cubic or in the hexagonal cubic packing, you will get a packing fraction. What is packing fraction? A packing fraction is the volume occupied by the objects, which in this case is candies, to the volume available for the candies, which is the volume of the vessel. That fraction is going to be 0.74. No quarrel in this number. This is for well-prepared structures and supposedly for infinitely large approximation. If I give you a finite container and I don't follow any of these prescriptions to pack, it's going to have a packing arrangement which people call as a random close packing. Okay? Random close packing, nobody knows the answer. Nobody knows the answer. What is the answer? Forget random close packing. Is 0.74 the best packing one can get using a sphere? Does anybody know that as an answer? You can write down, is this the closest packing? Yes or no, you can write it because I'm going to give you the answer. The answer to this will stagger you even more. The answer to this has been, predicted or given out by Johannes Kepler. Johannes Kepler said that, yes, this is the thing. It's called Kepler conjecture, but nobody has proved it. The proof which we attribute to Thomas Hales came in 1998, and this proof has not been checked. Okay. If you put balls in very proper arrangement in the hexagonal cubic or face-centered cubic, 0.74 should be the answer, is just not completely, solved. What are we talking about? We think that we understand so much math, we are able to send rockets to Mars, we know so much about artificial intelligence, but this simplest math problem has not been proved by experts. That's where we stand. This is for the young physicists up there. Okay, now we will move on. Let's take random close packing. We need to live with random close packing because we cannot always arrange things. So we think we understand a lot using packing fraction. It is not so, and we always have to pay attention to these granular media and how they are able to jam, meaning that a configuration where it's not going to move much. It's not going to move at all. That's the jamming point. And the jamming point is of great interest because fundamental level and application level it's of great interest. Okay. I'm not going to do too much here. I'm going to show you the three-dimensional phase diagram again, just for the interest of people. You can describe almost any solid object, interaction of solid objects using this phase diagram. And that can give you whether the configuration is going to be stable or unstable, jammed or unjammed. Okay. And this is something which is recent. It's very interesting and very relevant, and relevant in many areas, starting with grains to that of traffic. Now, here is another example where you can use grains to come up with new innovative ideas. Okay. If you take a regular robotic arm, you want to pick a pen, it'll struggle. If you want to pick up a cutting plier, it'll struggle. Now, the most difficult object is this pyramid here, which all of you can see, the pyramid, which is here. Okay, I'm just circling here. This pyramid structure is the most difficult thing. Even our arms cannot grasp it so well. Now, this kind of a gripper, which is designed by University of Chicago physicists, it's using the principle of jamming. You know, you put in grains and you vacuum it. After it's going and holding the object, it's going to grip it, and then you can lift it off. So this is a robotic gripper, which is also taking new dimensions in innovation. Okay, I'm going to switch gears and quickly go to various other opportunities where the modern developments of chemical engineering can bring in. And maybe I'll just skip this section because it might take a little more time. One thing I'll tell you is if you start mixing powders in a tumbler, you'll see all these beautiful patterns. And this patterning can be understood. Okay, I won't go into the reasons why these patterns are appearing and how they change with humidity and all. But that patterning has something to do with the traffic jams. Because traffic jams is quite incessant. I don't know how Tirunelveli city is coping up, but Chennai is definitely a big mess when it comes to traffic. Now, we did use in one of our studies to model this traffic jam using the analogy of the granular media, and we were able to get a beautiful matching, beautiful link between this and this. We were able to see patterns, and the other side you will see traffic. So all kind of things are possible because we are taking the most simplest approach and try to extrapolate it carefully. You can understand a lot of good physics. Okay, this is the patterning thing, which let's just skip for a moment. So bottlenecks in granular flow directly is linked with jamming in highway, right? This is something which we have to acknowledge. I'm going to show you one movie which is something which we didn't expect when we read the paper first. We were quite surprised. The movie will show you that for creating a traffic jam, you don't have to have higher density. Meaning, if there is a bumper-to-bumper traffic on the road, then you will expect a jam, right? But this is an experimental thing. Study conducted in Japan, in Tokyo University, where they found that you don't need to have that higher density of vehicles to create the jam. You will see that the cars are circling with sufficient space in the front and in the back. As the movie proceeds, you will see that all of a sudden, small mismatches in the acceleration, decelerations, cars tend to stop, come to full stop in regions, and then that's called jamming, and then they get unjammed. You can see already it's happening. right? Already you can see that it comes to a standstill and then it releases. So this is called jamming and unjamming. So this is completely a rich area. I'm going to stop here. A few more slides. This is a rich area, traffic study, and with the autonomous vehicles, driverless vehicles, which are going to come in the future, the physics of traffic jams is going to be quite an important thing. And I think with the time in mind, I'm going to skip some of these slides and I'll tell you what how the modern developments in experiments in complex systems came forth. It is attributed to one of the legendary physicists, Harry Sweeney, who said that you don't need huge, complex. Let's just avoid the word complex because you might just feel intimidated with complex cropping up everywhere. You don't need expensive equipments to study rich physics. Higgs boson discovery is not all, right? You can use simple tabletop experiments to study new physics, to discover new physics. And that was his philosophy. And he did contribute a lot to the study of complex systems. And in that direction, in my career, I have studied a lot of experiments, simulations, theory. These are some of the glimpses what I have been involved with, different stations in my career. And this is also an ongoing project. One of the ongoing projects is studying time theories and what are the hidden structures in it. Okay, so without much ado, I would like to just summarize some complex systems. The fundamental entities are simple ones that interact, and then rich behavior comes in. And for the benefit of students, they should know that you don't always have to go to something like higher energy physics or even complex systems. Even simple problems in physics are still unsolved, like the three-body problem. And collective behavior of individuals gives rise to these rich behavior, like flocking. And flocking can help us to know much about our own body, about financial markets, about various other networks. And networks I didn't even talk about because of lack of time. But essentially, very many things are there in the complex systems study. And we also saw some real-life applications between seemingly unrelated things like the granular media and the traffic. Okay, so with this, I would like to thank you all for your patience. I'm going to stop for questions. Thank you.
Could you please explain ergodicity again?
Participants, you may unmute and raise your questions to Dr. Nirmal Tyagu.
Yeah, I hear someone raising a question. Yes.
Yeah, I was asking, could you please explain ergodicity again?
Ergodicity is a technical term for which trajectory in phase space in the PQ space can literally go everywhere that is available to it. In possible, there's no restriction to where it can go. If you look at the simple pendulum is not ergodic because it cannot go to all regions. Okay, but a double pendulum is almost ergodic within the phase space. And it might resemble noisy thing, but it is not noise. It is deterministic system.
So we can come up with a deterministic equation for all, complex systems. That's what the first point was.
That's a good question. If we can model something close that resembles, we have to keep modeling. See, that's what I showed the Lorentz system if you have atmospheric weather. And Lorentz system is something that wanted to replicate one or two essential features. We cannot completely model the weather system, but he was very successful in capturing the essence. So yes, the attempt should be made to capture most of the features, and we may not know the equations. Yes. Deterministic equations should be the one which which our goal should be.
Thank you.
While I wait for questions to come, I want to show a couple of more slides for the benefit of students and participants. What some of you might have this question as to what are the skill set required for the students in order to excel or in order for you to enter and see. So the basics remain basics. Physics, math, or hard sciences, whatever software engineering, whatever artificial intelligence, whatever data science, all that fancy things come in. Hard sciences like physics and mathematics will always be there even 500 years from now. So please tighten up your math skills, study differential equations, first order, second order, study partial differential equations, heat equation, wave equation, diffusion equation, how to solve them, what are the boundary conditions, all that. It's going to be terrifically putting you in a good place. Number two is programming. Math is essential. Programming, you can take up MATLAB. MATLAB is a licensed thing, so you can go for Octave, which is open source, free, just like MATLAB, or you can go for Scilab. The equally important development and exciting thing is Python. You can go for Python and study NumPy. This is going to really, really help, and every student who comes out of BSc should know some language on their own. Don't blame it in the institution, because that revamp will take some time for the colleges to pick up, but start your own self-study, because enormous amount of sources are there, online and offline. You can go for that. Okay, skill sets wise, math and programming is a must. And how to keep yourself updated? Resonance magazine, which is free. Indian Academy of Sciences publishes it. Go to the website, download it. You'll have constantly every month something coming in. Quanta magazine, subscribe it online. Physics World IOP, subscribe it online. Free, everything is free. If you are reluctant in understanding, like, should science be my career pathway, go and download this free book by K.R. Srinivasan from ICTP in Italy. He has compiled interviews from 100 scientists who are, many of them are Nobel laureates. So please go and see if anybody, needs to know why you would need to be a scientist. So it's a terrific book. Please go and do that. And some last penultimate tips for you. If I may take one more minute, ask a lot of good questions. Okay, that's what Rabbi was taught. His mother, after he comes back from school, will ask, "Did you ask good questions in the school?" And that's what Rabbi is saying, that gave him this pathway to enter physics and excel. So he's a Nobel laureate. And our own C.V. Raman, he asked a lot of questions. So there is this famous lecture he gave to school students available on the web. You can go and download it. One thing which you can take home, a takeaway message in this talk, you can say, is that if you want to really understand something, you need to ask a lot of questions. So, C.V. Raman's case, you have to ask why the sky is blue. Now, how do you answer this question? How do you answer any question? The way to answer any question is by asking another question. And then you ask another question. Why the sky is blue? So you have to ask that, is the sky blue all the time? Is the sky blue at night? Is the sky blue in the mid-noon? Is it blue in the evening? Is it blue in the morning? If it's cloudy, is it blue? What time of the day is it more blue? Is it because of the intensity? Is it because of the wavelength? So you can keep asking these questions, and then one day you can win a Nobel Prize. So that's the message which C.V. Raman passed on, and I'm going to stop here. If any questions are there, I'll be glad to answer.
Thank you, sir. The essence of all beautiful art is gratitude. Here comes Dr. J. Juliet Lada Jaykumari, Assistant Professor of Physics, Saratagar College, to propose the vote of thanks.
Good morning to all. It's my privilege to propose vote of thanks on this occasion. Let me first of all start by giving glory to the Almighty God for making today's webinar a resounding success. Our heartfelt thanks to our distinguished speaker, Dr. N. Nirmal Tyagu, Assistant Professor of Physics, Madras Christian College, Chennai, for making an excellent presentation and making this webinar a meaningful and interesting. Sir, we got a clear idea on simple pendulum, double pendulum, 2 and 3 body problems. The videos on simulation is very much interesting. The real world examples and colorful pictures are appreciable. We are extremely grateful to you for your insightful presentation, sir. Next, I would like to express our deep gratitude to our respected Secretary, Reverend Soundrapandian Ayya, for his support and encouragement. I would like to thank our principal, Dr. Usha Godwin, for her support, vision, and commitment. I would also like to thank our beloved HOD, Mrs. D. Jagati Jasmine, for her moral support and guidance in all our activities. Our special thanks go to Dr. T. Vardhini, Associate Professor of Physics and Organizing Secretary of this program, for her valuable contribution. I am happy to express vote of thanks to our staff members and all the participants from other colleges and from our college who have made it a success. Thank you, one and all.
Okay. Thank you all for your patience, and I really enjoyed this talk. Thank you.
Thank you, sir.
Thank you, Juliet ma'am. Thank you, sir. Dear participants, kindly fill the today's feedback form. The link is posted in the chat box. Today's session has come to an end. We shall meet tomorrow at 10 a.m. for the final session of Recap 21. If you have submitted the feedback form, you may leave